Okay, we're going to just have a few minutes on osmosis. And osmosis is something that you're pretty familiar with from high school. For some reason, one of the key issues seems to be that it's very much a misused term in general vocabulary. What we're talking about is movement of water, and water only. So you can't absorb knowledge by osmosis or anything else. Nothing else is going to move by osmosis except water. So, defining osmosis, I think you should get yourselves onto Quizlet. Osmosis is defined as the net movement of water. And here we're going to meet a bit of terminology, and it's from an area of high water potential to low water potential. So we're talking about high water potential. Now this is a term that you have not come across before. And at the high school you will have done water concentration and done it as a specialised diffusion, and it kind of is, but we call it a water potential now that we're grown-ups. Water potential, you can give the symbol psi. I know that the psychologists have adopted it. It is the Greek letter psi, psi, so they like to claim it, but it belongs to biology. And we often see it superscripted as W or cell. So that's referring to the cell itself. Now, water potential is the tendency of water to move out of a system. So, if you've got a high water potential, it means a high tendency to leave. So solutions with high water potentials are going to effectively, the water's going to leave and go to somewhere where it's lower. And because in the case of osmosis, it's in diffusion, we're looking, although it's a passive process, it doesn't use any energy, we are always looking at it going across the membrane. So if you've got a beaker and you separate it out into two halves with a membrane, it's a comparative term. On one side you're going to have a high water potential, on the other side you're going to have a low water potential, and the water net movement is going to be that way. Of course, it's diffusion. If water molecules collide with the membrane, they're going to skip back across, just like in diffusion, but they're just going to not go as far, as much across. They're going to be more leaving and going into the low water potential solution. So they are all comparative terms. We're always talking about two sides of a membrane. Now, the other thing about water potential is a negative value, and this can often throw people. So pure water, if we've got just water, the highest number it can, water potential can be is 0. This is pure water. And then as we go more negative, the water potential is lower. So you need to be a bit familiar with negative numbers. So for example, minus 100 is a bigger number, a higher number than minus 340. So it's a negative value, so the more negative it is, the lower the water potential is, and the more likely the water is to be moving into it. The closer it is to 0, the higher the water potential, the more likely the water is to leave. And the units are weirdly a unit of pressure, which is the kilopascal. And that's because if you have a sort of, little funnely arrangement with a little semi-permeable membrane around the bottom, and you put in distilled water, highest one, and you've got your solution there, the water, the net movement is going to be in, and it's the pressure that you would need to apply up here to prevent the water having that tendency to move in. So once you get the water to stop, that's the pressure, which is why it's in kilopascals. You must remember to put the units on. So what would make the water potential get lower? Well, adding solute will do this. Now, a solute is anything that will dissolve in water. So we're talking sugar, we're talking salt, small soluble things, amino acids would happily lower the water potential of a solution. And the thing about solute is that solutes are polar. So they have an uneven distribution of charge, or, for the salts, they've got a great big fat ionic charge. And therefore, when you add solute to water, the water, because it's polar, and it'll rush to make friends with the solute, and it will surround it, make a little shell of little water molecules all going, I love you, I love you, I love you, you're charged, I love you. That takes out the free water from that solution. So those water molecules are not now able to contribute to the water potential because they're too busy loving the solute. So the free water molecules will decrease in number, and this will lower the water potential. So we also refer to something called solute potential, which is psi S, which is the solute contributing to that water potential. And again, it's a negative value. So the more solute you've got in, the more negative that value will be. So I think that deals with solute. So we can deal with how this affects cells then. So experimentally you will have done the potato mass experiment, and you will have done the plasmolysis experiment. Now there are other experiments that we could do, and the animal tissue that is beloved of A-level biologists are red blood cells. They handily come in their own liquid. So if we're looking at animal cells, animal cells don't have a cell wall. So if we put an animal cell into a solution that has a higher water potential, so this means that the one inside is a lower water potential than the outside, the water, net movement of water, will go in. In red blood cells, which you know are donut shape, they entertainingly expand to balloon shaped, and then they burst. And they release their red pigment, so then if you can centrifuge it, pull all the red blood cells into a pellet, any intact cells into a pellet at the bottom, the solution above will be full of red hemoglobin, and you can stick that into a colorimeter. If we put them into a solution that has a lower water potential, so it's got lots of, and you usually use salt for animal cells, so this is a solution with a lower water potential or a higher salt concentration, the water will move out and the cell will go wrinkly, which is called crenation. So as the water leaves, it will sort of almost collapse in upon itself. So what happens if we put our red blood cell into a solution that is isotonic, that has the same water potential? Well, the water doesn't stop moving for a set-off. So what we say is that it's at equilibrium and you've got an equal rate of movement in and out. Now, I did mention this term isotonic, I just kind of threw it out there. Isotonic, all the words that end in tonic. Tonic refers to solute concentration. And only solute. So iso means the same. So isotonic, same solute concentration outside and in. Hyper means more solute. So there, of course, we're talking about the solutions having a lower water potential. And hypo means less or under. A hypocaust is under a Roman floor, and therefore they have got higher water potentials. Now, the Book of Biological Nomenclature, published by the Society of Biology, suggests that you should only use those terms for animal cells, but they are pretty generally used, so you might see them used in the context of plant cells as well. So remember, comparative. So you always need to say which solution, which has the higher water potential, which has the low. It's always going to be moving from high to low. In animal cells, because there is no cell wall, pretty much the water potential of the cell is equal to the solute potential of the cell. So that's nice and easy to remember. But we're going to talk about plant cells now, and plant cells have this the cell wall running around the outside of them, and that just puts another layer of complexity into the whole thing. So if we look at the same situation, so our same thing, we're going to do the same thing to our plant cells as we do to our animal cells, and we're going to put them into solutions of different water potentials. I'm just going to draw a plant cell. And the plant cell has its cell wall around the outside. Now the cell wall is fully permeable. It's not going to be a barrier to anything. All it is something that is fairly lends structural support, and it's pretty inelastic stuff. It's not going to expand overly much. It's it's a bit like your suitcase. You can only stuff your suitcase so far before it starts to kind of bulge, but it's not going to give way. And you then have to take something out, don't you, to if you're going to put your hair straighteners in or whatever. So we've got a tonoplast on the inside, so we've got a two membrane system as well. That's a bit complicated, and we've got our cell membrane just on the inside of that. So if we put our plant cells into a solution, and we tend not to use tonicity for plant cells, into a solution with a high water potential, that water is going to cross straight through the permeable cell wall and into the cytoplasm and into the vacuole. And they're going to swell up, and they're going to push the cytoplasm. So it won't be the vacuole, but with cytoplasm pushing against the cell wall. This is where you're stuffing your suitcase full. And then your mum says, "Oh, can you squeeze a jar of coffee in there?" And the cell wall is inelastic, so it pushes back, and a push force is a pressure, and the old term for it was wall pressure, and we now call it, just to link in with all the other potentials we've got, a pressure potential. Now the difference between a pressure potential and the other potentials we've come across is that this is a positive value. It's pushing, so it's going to be positive. If we put our plant cells into a solution that has a low water potential, so lower than the plant cell, our cell walls are pretty pretty rigid structure. So we've got a cell wall around the outside of our cell. We've got our cell membrane, and we've got our vacuole. So I'm just going to draw that bit of cell membrane there just to remind you that it's there. And if we put it into a solution of lower water potential, water's going to leave the vacuole and go to the outside. It's going to leave the cytoplasm and go to the outside, and the volume of the cytoplasm is going to fall because the cytoplasm is mostly water. And as it falls, it's going to pull that cell membrane away from the cell wall. And that wall pressure is going to disappear because there's nothing for the wall to push against. The cytoplasm is not pushing against it, it can't be pushing against the cytoplasm. We call this sort of cell plasmolyzed. And the pressure potential is 0. How you spot this down a microscope is you can see a very clear gap between the cell membrane here and the cell wall there. So you've got this gap. Now obviously the cell wall's fully permeable, so whatever's on the outside of here will be in there as well, because this is the membrane for osmosis to be taking place across, and that's where the osmosis is happening, nowhere else. Now there is a condition called incipient plasmolysis. So I said that we'd be talking about tissues. Pretty much every single cell in your body and every single cell in a plant has its own water potential, and it's around the average. So when we're talking about tissues, we're kind of talking about the average water potential. So if we were looking at the red blood cell experiment, and we've got our salt concentration, and the percentage of burst cells, say, at low concentrations all of them are going to burst, then we're going to get this sort of steep bit in the middle where they start to burst. Some of them are bursting and some of them aren't, because they've all got their own water potential, so they all burst at slightly different. And then there'll come a point where none of them have burst because the salt concentration outside lowers the solute potential and water potential enough that they're all losing water. And so you might want to sort of take let's say if we want to work out the water potential, we might want to take that to be where 50% have burst. Half of them have burst, and that would kind of give us an average. It's kind of the same with the plant cells. So if we're looking at plant cells, you'd be looking at using sugar concentration. You usually use sucrose. And at the low concentrations, none of the cells are plasmolyzed, so you'd be looking at plasmolyzed cells. And you can spot these down a microscope. You count all the cells and then you count the plasmolyzed ones. And at the low sugar concentrations, there were many of them, and then there'll be more and more and more and more and more. And again, we take that point of where the water potentials are equal at 50% plasmolysis. So that's kind of an average for the tissue. 50% plasmolysis is the point at which we say the cells are in incipient plasmolysis. They're about to all be plasmolysed, if you like. And again, the pressure potential is 0 at that point. When we're looking at potato tissue, beetroot tissue, sweet potato tissue, whatever tissue you want to look at, with the mass experiment, remember at the low concentrations it gained mass and then it loses mass. That point of sort of equal water potentials is where there's no change in mass. So above this, the tissue itself is gaining water because this solution has a higher water potential. Above that concentration of whatever it is using, sugar usually, then the potato tissue is losing mass because it's losing water. Where there's no change in mass, no gain or loss of water, that's what we say the water potential of the tissue is. Now obviously all these concentrations are usually in moles, but our water potential is in kilopascals, so you also need a table to convert one to the other. So this cell wall kind of alters the relationship because the cell wall will actually prevent, the pressure will prevent more water entering even if you've got solute inside the cell. So we have another equation for plant water relations, which is the water potential of the cell is equal to the solute potential, which is negative, plus the wall pressure, which kind of resists that. So we've now got another situation where the cell wall is, the cell's as full as it can be and it cannot physically take in any more water, then the water potential is going to be 0. So pressure potential 0 at incipient plasmolysis, or where there's no net movement of water. Or where the water potential outside equals the water potential inside the tissue. This is going to be 0 at full turgor when the cell actually physically cannot take in any more wall pressures at its maximum. In which case, obviously, these are two negative values. Remember, you do need to be able to rearrange this equation. If we're looking at that being 0, then these two numbers are going to be the same, but this one's going to be plus and this one's going to be minus. Okay, I think you need to probably practice doing a bit of formula rearrangement and a few calculations with that. Good luck!